So welcome back in our new class. Today I am going to start new chapter Electromagnetic Induction. The phenomenon in which electric current is generated by changing magnetic fields is known as electromagnetic induction. So the current so produced is known as induced current. If current is induced in the circuit, this must be due to EMF produced in the circuit. This EMF produced as a result of change in magnetic field is known as induced EMF. This phenomenon of electromagnetic induction is the basis of working of power generators, dynamos, transformers, etc. Now, magnetic flux. Magnetic flux. The magnetic flux through any surface held in magnetic field is the total number of magnetic field lines of force crossing through the surface normally. Generally, magnetic field is denoted by phi or phi b. This b denotes magnetic field. Suppose this is an area A and magnetic field passes through this area, that is B, and B is normal to the area. So magnetic flux, according to the definition, is the total number of magnetic field lines of force passing through the surface normally. So phi is equals to BA. That means product of magnetic field and that area through which passes. But here we will see both magnetic field and area are perpendicular to each other. Now suppose if we are going to find out the magnetic flux when the magnetic field is not the normal of the area. So here we will see this is here the uniform magnetic field lines and this is here area A, magnetic field lines B. We are going to see here now. If suppose the magnetic field B, this makes an angle theta with the normal drawn to the area A. This is here normal unit vector. Then component of magnetic field in the direction of the normal to the area A, that will be Bn in this direction. Bn will be also in this direction. This will be equals to the component of B in this direction. This angle is theta. Then Bn, this will be equals to B cos theta. So B cos theta is the normal component of B magnetic field, which is actually perpendicular to the plane of this area. So here we know here this Bn is equals to B cos theta. This equals to B cos theta. So magnetic flux phi, that will be equals to Bn, that magnetic field, into the area through which passes. Bn equals to B cos theta into A, and this equals to BA cos theta. Now BA cos theta, that can be written as B dot A vector. This is area vector. So direction of area vector A is the direction of outward drawn normal of the outward drawn normal to the surface. Thus magnetic flux through this given surface is the product of the area of the surface and component of magnetic field along normal to the plane of the surface. Now we have some conditions. Suppose angle between B and this normal is 0 degree. Now in first case, if theta is equals to 0 degree, that means uniform magnetic field is acting perpendicular to the plane of the surface. Then phi will be equals to BA cos theta, and this equals to BA cos 0 degree, and we know very well cos 0 degree equals to 1. So this value will be BA. This value is 1. This value is BA. This will gives you the maximum value of magnetic flux when both B and A are perpendicular to each other in the. Now we will see, suppose this is here area, then what will happen if theta equals to 0 degree? Direction of magnetic field in this direction, normal vector in the same direction. Here we will see, then phi, value of phi will be here positive value. Now we will see when theta equals to 90 degree. Theta equals to 90 degree. 90 degree, that means uniform magnetic field is acting along the plane of the surface. In this case we can understood this one. Suppose this is the blue board and direction of the magnetic field is in this direction. board here and it is also in this direction. If it is like that and magnetic field passes through this, then they are perpendicular. When it is like that surface and magnetic field is this, when both are at the same, at 90 degree. So here we will see theta equals to 90 degree. Then phi equals to BA cos 90 degree, and we know very well cos 90 degree equals to 0, so its value will be 0. So here we will see when magnetic field is acting along the plane of the surface, then value of the flux will be 0. In the third case, we will see when theta equals to 180 degree. So that means uniform magnetic field is in this direction and direction of the normal in this direction. We will see here now in this diagram. This is here the area A. This is the direction of the magnetic field B, and here is the normal on this plane of the area. This is normal vector. Both have 180 degree. Then in this case, we will see phi equals to BA cos 180 degree. This equals to minus 1, value of cos this minus 1. This equals to BA. This equals to minus BA. Then we will see in this direction phi will be what? Negative. Phi will be negative if angle between A and A is 180 degree. Now we are going to find out the flux of a non-uniform surface. Suppose an area of the surface, this is, and magnetic flux passing through this here, uniform magnetic field. B, and area of this surface is suppose A. So first we consider here a surface and magnetic field B, and here we divide this whole area into a number of small area element that is denoted by dA. So this is here the small area and it's dA, and normal on this one is unit vector n. So magnetic field may be assumed as uniform over this surface, and if theta is the angle between B, this, and component of B to the in this direction, and this will be here now. If this is the direction of B, this is the angle theta, then in this direction magnetic field will be B cos theta. So magnetic flux through this area, we will find this. After that we will integrate for the whole area. So magnetic flux through this small area or a small area element dA, this is suppose d phi. So d phi will be equals to that magnetic field in this direction, that will be suppose Bn in the direction of n normal, and its area dA. We know very well Bn is equals to B cos theta. And into dA. This is here. So we can write this. This is B dA cos theta. This may be written as B dot dA. This is here the magnetic flux through this small element. This. Now we are going to find out the total flux through this whole area. Then flux, this will be integration of this, integration of d phi and over whole surface A. This may be written as integration of B dot dA. I think it is very clear. Now we know very well then phi equals to BA. From here we are going to find out that a magnetic flux density. So this magnetic flux density B equals to phi by A. So this can be said as the magnetic flux density B as the magnetic flux associated with the unit area of the surface. Second thing, we are going to say about the SI unit. SI unit of magnetic flux, it is Weber and it is abbreviated WB. So 1 Weber is equals to that 1 Tesla, that is the value of magnetic field, into area 1 meter square. So this can be written as 1 Tesla meter square. So 1 Weber is equals to 1 Tesla meter square. So we can say 1 Weber is the magnetic flux linked with a surface area of 1 meter square when held normally inside the uniform magnetic field of 1 Tesla. We are going to see here now CGS unit 2. CGS unit of phi magnetic flux. So here this is its SI unit is Maxwell. And it is denoted by mx. Mx here. So here we can say 1 Maxwell is equals to 1 Gauss. Gauss is the unit of magnetic field in CGS unit into 1 centimeter square. So 1 Maxwell is the magnetic flux linked with a surface area of 1 centimeter square when held normally inside a uniform magnetic field of 1 Gauss. Now we are going to say that what is the relation between Weber and Maxwell. Relation. Relation between Weber and Maxwell. So we know very well 1 Weber equals to 1 Tesla meter square. That means 1 Tesla is equals to 10 to the power 4 Gauss, and 1 meter square is equals to 10 to the power 4 centimeter square. 1 Tesla meter equals to 1 Tesla into 1 meter square. This equals to 10 to the power 4 Gauss into 10 to the power 4 centimeter square. This value from here, this value from here. So this equals to 10 to the power 8 Gauss centimeter square. So 1 Gauss centimeter square equals to 1 Maxwell. So this equals to 10 to the power 8 Maxwell. 1 Maxwell is equals to 1 Gauss centimeter square. So I think it is clear. Now we are going to discuss some experiments, and I remember that it is also discussed in the 10th class. That is the Faraday's experiment. Faraday's experiment. Remember now, we are going to discuss here now some different processes. First, the production of EMF with a stationary coil when a magnet moves. Means coil is stationary and magnet moves. Suppose this is a loop coil and this coil is connected to a galvanometer. You know about the galvanometer from the previous classes that can detect the current in this circuit. We will see when a magnet, a bar magnet, is brought towards this coil. So we will see the magnetic field lines passing through this coil is here in this direction. But this magnet is always in motion. Suppose its velocity is v. This is the constant velocity. It is moving in this direction. Then we will see there is a deflection in the magnetic galvanometer, and we will see this. But when this coil is placed like that here now in the same way, but this time this magnet which has these two poles, north and south pole, moves away from this coil. Here we will see as it moves in this direction, the number of field lines passing through this that decreases. So here we will see magnetic field lines decreases. Magnetic field lines is more here, and here it we will see that decreases. But in these both cases, we will find the deflection in this one and in this one. If it is moved in this direction, suppose deflection is here in this direction, and when it moves away from the coil, we will see deflection is in this direction. So here we will see direction of EMF produced in this coil and in this coil is opposite. So here we will see current is flowing in this direction, then current is flowing in opposite directions. So we will see when there is a motion between coil and the magnet, we will see that a current is induced in the coil. One more thing, we will see if the coil and the magnet both are stationary here, then we will see there will be no change in magnetic field lines crossing this area. So we learn here then EMF is induced or current is induced in a coil when there is change in magnetic flux passing through the coil. Second example, we have here now two coils, one coil, and through which some supply is given, some current is given. Here is the tap key, and here is the another coil which is connected to galvanometer. Now what happens? We can say here now production of induced EMF with stationary magnet, when the strength of the magnetic field is varied. Here now in this portion we will see we will supply the current, and this is here the another coil through which galvanometer is attached. When we switch on, we will see there is a deflection as we make the switch on, and when it is continuously on, then we will find there is no deflection in the galvanometer. When we make switch off, then we will find there is again deflection in the galvanometer. Here we will find during making switch on or off, there is change of magnetic flux passing through this coil. So when we switch on this, we will see that through this coil a magnetic field is established which passes through this, and when switch is on, we will see there is no change in magnetic flux passing through this. So at that time we will see there is no deflection. When we make it switch off, we will see there is change in magnetic field lines passing through this from maximum to zero. So here you will find there is a deflection again in the galvanometer, but in both conditions we will find that deflections are in opposite direction. In the same case as the third, now this time magnet is kept stationary, and coil which is connected to a galvanometer is made movable. So coil is moving and magnet is stationary. So velocity of or speed of the magnet is 0, and suppose it is moving in this direction, then we will see deflection deflection in one direction, and when it is moved in this direction, deflection is in opposite directions. So here we will see if there is a relative motion between magnet and the coil, an EMF is induced. So this is here our today's class. Thank you.